Okay, actually this document is something we did in class as a whiteboard review. You practiced some of these problems. For the top section of this, it was just reminders of things we looked at in the book. There's a good summary of the entire chapter. Each version of factoring is on page 509 of your textbook. Um, Basically what it says is regardless of which section you're in, regardless what the problem looks like, you're going to want to attempt to factor out the greatest common factor. What that looked like is a real easy version of it. If you had 3x plus 9, you could pull out 3 out of each of those pieces. If you divided the first piece by 3, you get just a 1x. If you divide the second piece by 3, you get a 3. We said you're factoring out the greatest common factor. We also thought of it as the reverse of the distributive property. It's supposed to multiply the 3 into the parentheses. You're really dividing the 3 away from each part. Okay, then whether that version works or not, it doesn't matter. You still have to attempt other versions of factoring because there's some problems, you're going to be on the test, some problems we've already had that have more than one version of factoring that can work. So it's just based on how many terms are in the problem after that. So if I wanted to see if what was left over on the inside of this could factor, well, first off, it has 2 terms, and other than the GCF version, the only other version that works for 2 terms is the difference of squares. There's actually a typo. I was going to put it's the difference of squares, and I want you to look for the square roots of each piece. Okay, you know x is not a perfect square, 3 is not a perfect square, so that doesn't work. So on that first example I just showed, all you can do is factor out the GCF and you're done. But some problems, you're going to be able to find the square roots if there's 2 terms and go further with it. And you'll see that below. If there happens to be 3 terms, technically there's 3 options to choose from. But this first one is just a shortcut that's not necessary for you to learn or for you to master. It just makes some problems go quicker. I really just want to focus on the bottom 2. They have a similar approach in parts of the problem. It really depends on whether there's just an invisible 1 in front of your x squared, or this a value represents some number being in front of x squared. In this example, I have that a value is 12. If there's a number in front of x squared, that is the method that requires the work. Usually it takes us about 4 lines of work to get to the answer. But if there's no number in front of x squared, like this problem, you can just think of numbers multiplied by 6 and added by 5. In that case, numbers multiplied by 6 added by 5 are 2 and 3, and you can just fill in your parentheses with the appropriate numbers. In order to get started on this one, we took 12 times negative 5. You got a negative 60 off to the side, and from that negative 60, you wanted numbers that multiplied to be negative 60, but added to be the 4 that was in the middle of your problem originally. You couldn't go straight to the answer there. There's a lot of work. You'll see that below here. I'm going to try and quickly get some examples on here. I might not do every problem, but try and pick at least one from each type of problem. And there was really a fourth option, other than the GCF, 2 terms and 3 terms. You could have 4 total terms in your problem, and if we were doing that, we like to really group them. It's called factor by grouping, and then treat it very similar to just factoring out the greatest common factor. What's in common in the first 2 terms, factor it out. What's in common in the second 2 terms, factor it out. And we eventually showed another line of work or 2 in there and got down to the product of binomials, which is what most of our answers look like. A binomial times a binomial, and all these versions of factoring except for sometimes a GCF didn't look like that. Okay, so an easy problem to get started with. Regardless of the problem looks like, try to factor out a GCF. In this case, 6 goes into both of those numbers. Divide it away, you just get an x squared. And divide the second spot by 6, you get a 9. That's as far as you can go with that GCF version. Then there's 2 total pieces, and you want to see if this can break apart. In order to use that concept called difference of squares, it really literally has to be a difference. Difference meaning subtraction. So if I needed to look for the square roots of these numbers, that method could work on this if it was x squared minus 9. If it's x squared plus 9, there's no way to go any further. So I don't really need to think about square roots because it's not actually a difference of perfect squares. That is your final answer. Can't go any further. Next problem. Remember, regardless what it looks like, regardless what directions are telling you, if there's any mention about factoring, you look for a GCF first. 2 goes into every one of those numbers. You factor that 2 out, get an x squared, a 6x, and a 5. Okay, now let's just concentrate on the trinomial that's inside of the parentheses. If there's 3 pieces, we had a couple different versions of factoring, and you got to think about which one. We're going to choose the one that has nothing in front of x squared, nothing other than the invisible 1. So that version is the one you didn't have to show any work. You just had to think of numbers that multiply to be 5. In this case, very short list to choose from because 5 is a prime number, and add to be 6. Those numbers multiply to be 5 and add to be 6, so you can go straight to your answer. X plus 1 and x plus 5. Just fill in the second spot in each parentheses with the numbers you came up with. The first spot in each parentheses is put your variable. Your variable is x most of the time. And I'm going to drop down the 2 that was attached to that originally. So there was 2 methods of factoring that worked in one problem to get it completely factored. You can't just do one or the other. You got to do both. But always look for a GCF regardless of what the problem looks like. Problem number 3, you take a look at it. Factor out a GCF. In this case, it's possible again. You gotta think a little bit. 2 goes into all the numbers, but 4 also goes into them. 8 does not, so we're going to choose to factor out a 4. Leaving behind a 2x squared, a 3x, and a 6. Really, that process is just you dividing away the GCF. Write the GCF in front of the parentheses, and divide each piece by it. Okay, what's left inside of here is a trinomial. Has 3 total pieces, and we want to see if we can factor it. Because there is a number attached to your x squared, really what you got to get started with is taking the first number times the last number. That product is 12, and then you want to list factors of 12 and see if you can make a combination that adds to be 3. You got 1 and 12, 2 and 6, 3 and 4. None of those pairs can add up to be 3. So that's how you know you actually were done with the problem. Your answer was just factoring out the GCF and leaving that trinomial in parentheses. You can't break that apart any further, but it's worth taking a look at because sometimes you can, like in the previous problem. Number 4, try and factor out a GCF. There's a 2, an invisible 1, and a negative 21. There's no number that goes into all of those except 1, so there's no number you can take away. They don't all 3 share an x. Only 2 spots have the x. So no GCF can be taken out. You got to rely on, well, there's 3 pieces, so I'm going to go up to my methods, figure out which one will factor this trinomial. Because there's something in front of x squared, I need to multiply the first and last number together. So off to the side, 2 times negative 21 is negative 42. I'm going to, real quick, come up with all the combinations that multiply to be negative 42, looking for the one that adds to be 1. Okay, you would have negative 1 and 42. Negative 2 goes into it. I should have a positive 21. Try negative 3, try negative 4, try negative 5. Come up with each combination individually. You're really looking for them to add to be a positive 1, so I go a little further. 4 didn't work, 5 didn't work. We do have negative 6 going into it 7 times, and I would have negative 7. I'd start repeating myself. Okay, those together add to be 1. This is the time-consuming type of factoring. I'm going to take what was a trinomial. I'm not going to touch the first piece and the last piece. Those are staying the same. But instead of having that 1x in the middle, I want the equivalent of 1x. Because I want it to really be the same expression, just have it look different. These together add to be 1, and they multiply to be the negative 42 I was needing. So I turned it into something that had 4 pieces. And from here on out is that factor by grouping type of factoring we were using. You just concentrate on the first 2 terms, factor in out of GCF. After that, concentrate on the next 2 terms, factor in out of GCF. And you'll eventually be able to take it down to a binomial times a binomial. 2x comes out of the first set of parentheses. Think about what's going to go on the inside. 7 comes out of the second set of parentheses. Think about what's going to be on the inside. 2x divided by 2x is going to be a 1x. Or sorry, 2x squared divided by 2x. So 1x. And negative 6x divided by 2x is a negative 3. 7 divided by 7 leaves a 1x. And negative 21 divided by 7 is also negative 3. If you're doing this method correctly, that's always going to happen right here. These parentheses are going to be identical. Don't take it for granted and just assume they are. Do the work. And then that was kind of a way to double check everything you've done. Okay. That identical set of parentheses you're going to write down one time, basically moving it to the front. And then what's left over is the 2 terms that you really factored out. That 2x and a positive 7 are what fill in your second set of parentheses. And you could check your work. You could do your 4 multiplications of foiling like we did last chapter. You get back to the original problem. So on the test, in theory, you have a way to double check every single problem. Either due to distributive property or foiling, which is just another version of the distributive property. You can always take what is your answer, if it's correct, and get back to the original problem. Problem number 5, I'm not actually going to work out. So you have 2 methods. You can use the square root method for the perfect square trinomials, if you know that. But like I said, that method is never necessary. It's merely a shortcut. The other option is, since there is no GCF, take 16 times 25, list off the side all the factors until you can come up with what adds to be 40. The one I actually want to skip ahead to is number 6. We haven't done a problem quite like it yet. Every single problem, look for a GCF. Does any number go into both of those? Well, no, because we got an invisible 1 in here anyways, and they don't share any letters. So what you need to be doing is going on to that list above, or page 509 in your textbook. If it's 2 pieces, it's a binomial. There's only 2 terms here. The only other version of factoring is the version of factoring that requires you looking at the square root of each piece. The square root of x squared is x. The square root of 100 is 10. And the reason why there is no middle term is because we were doing this last chapter. There was a binomial times a binomial. They look the same, except one had a plus sign and one had a minus sign. Which one doesn't necessarily matter. But in that foiling process, you would have one multiplication give you a negative 10x, a different multiplication give you a positive 10x, and there's 0 x's in the middle. That's why it goes straight from an x squared to a constant. Okay, that's just more of a way that you check your work. But x squared minus 100 factored out is going to be x minus 10 times x plus 10. Look for the square roots. Fill in your parentheses, one with a plus sign, one with a minus sign. I think I have 13 total examples in here, but this might be the last one I end up doing. Regardless of what the problem looks like, factor out a GCF. They both have a 5 that goes into them. They both share at least an x to the first power. If I take that away, I'm going to have an x squared, and 80 divided by 5 is 16. The x's are gone in that spot. I actually can go further on this, because that is just like the previous problem. I know the square root of each piece. Square roots are an x and a 4. I need 2 sets of parentheses. One with a plus sign and one with a minus sign. To continue to factor that out. Okay, that's going to be the last example I have, but it should get you seeing every single possibility that we've practiced so far.